This is our last video on rational functions, and in this example we're going to talk through in detail graphing a rational function that has a slant asymptote. So let's go ahead and kind of start there. Notice that this is a rational function, x squared plus 5x plus 4 divided by x minus 3, where the degree of the numerator is 2 and the degree of the denominator is 1. So you see that piece. You'll notice I'm leaving a space here. I'll explain why in a second. So note that the degree of the numerator is equal to 1 plus the degree of the denominator. And this is like super important. I guess I'll make this purple color. When you see this, that tells you that your function is going to have a slant asymptote. It's not going to have a horizontal one, but it is going to have a slant asymptote. Now, I left a space here because I'd like to write everything in factored form. X squared plus 5x plus 4 factors nicely. It's x plus 1 times x plus 4 over x minus 3, and so you'll notice that there aren't any matching factors in the numerator and the denominator. So we can feel comfortable that there are no holes in this graph, but now that we know about holes in the graph, we should always be on the lookout for them. Okay, so we're going to take the same approach that we always have. First, we'll talk about asymptotes. So we see that there's a denominator here, right, x minus 3, and so that tells us that we have a vertical asymptote, just one, when x is equal to 3. So vertical asymptote, x equals 3. No horizontal asymptote because the degree of the numerator is larger than the degree of the denominator, but there is a slant asymptote. And so I'm just going to remind you one more time that for the slant asymptote, we're going to write our function in quotient remainder form. So again, this function would lend itself to synthetic division. But because not every function is going to, some functions are going to have kind of a gnarlier denominator, we're going to go ahead and just use long division here. So we have x squared plus 5x plus 4, and we're dividing it into x minus 3. Good old-fashioned long division. So looking at the first terms, to get x squared, x must be multiplied by x. We distribute through, and then we subtract. So don't forget that we are subtracting and that negative has to get distributed through. So the x squareds cancel, but then you have 5x minus negative 3x. So you actually end up with 8x there, and then the plus 4 comes down. X times positive 8 would give you 8x. Distributing through, we have 8x minus 24. And don't forget, we are subtracting. So the 8x's cancel, and we have 4 minus negative 24 is 28. So there is my remainder. And there is my quotient. So if I wanted, and I do want, I can use this process to say that my function r of x is x plus 8 plus 24 over x minus 3. And this is my slant asymptote. Okay, so now I want you to remember that asymptotes, at least for our purposes right now, are lines. So we have a slant asymptote, which is the line y equals x plus 8. Slant asymptote. Okay, now remember, slant asymptotes are kind of in the same family as horizontal asymptotes, meaning that they also describe a virtual behavior. So eventually, I think I just said virtual behavior. I meant eventual behavior. So eventually, the graph will come closer and closer and closer to the slant asymptote. But much like the horizontal, a function may cross its slant asymptote. So I'm going to skip ahead and I'm going to start mapping out the graph, even though we still have intercepts and the sign chart to talk about. So I'm going to actually leave this whole space to the graph. Okay, so this will be my y-axis and my x-axis. And my vertical asymptote is x equals 3. Right, so there's that. And then my slant asymptote is the line y equals x plus 8. So this is a line. So we need 2 points to graph it, or you could use slope-intercept if you're comfortable with that. So it'll cross, the slant asymptote will cross the y-axis at 8. So let's map that out. 1, 2, 3, 4, 5, 6, 7, 8. And then it'll cross the x-axis down at negative 8. 1, 2, 3, 4, 5, 6, 7, 8. So there is my slant asymptote. Okay, now let's talk about intercepts. So intercepts will again take on 3 shapes. So we have our x-intercepts, and x-intercepts are points on the x-axis, meaning points where y is 0. So we're going to set the whole function to 0, and what I hope you remember by now is that when you set all of your function to 0, you're basically looking at where is the numerator going to be 0. So please pause the video and walk through this process on your own if you need to, but the x-intercepts are going to be at -1 and at -4. That is where x plus 1 and x plus 4 are equal to 0. So we can mark them here. There is -1, 0, and there is -4, 0. Okay, now for the y-intercepts. So again, y-intercepts are points where the graph crosses the y-axis. If the point crosses the y-axis, it means that the x-coordinate is 0. So we're going to plug 0 in for x. And again, what I hope you remember is that when we plug 0 in for x, only the constants remain. So we'll have the 4 on top and the -3 on the bottom, which tells us that the y-intercept occurs at the point 0, -4/3, which is down here. Okay? And then last but not least, right? So does this, or where does this function cross its slant asymptote? So imagine that it crosses it here somewhere. Well, the slant asymptote is the line, in fact, let's label it, y equals x plus 8. So any point on the graph of the slant asymptote, whatever its x-coordinate is, its y-coordinate is x plus 8. And you remember that when we were dealing with x-intercepts, those are points where the y-coordinate is 0. We set the whole function to 0 and we solved for x. Well, to figure out where it crosses the slant asymptote, we're going to set the whole function to x plus 8. So we'll have x squared plus 5x plus 4 over x minus 3. And we want to see if that's ever going to be equal to x plus 8. Well, this is a rational equation. And you all know that when we're solving rational equations, we can multiply both sides by the denominator. So I'm going to multiply both sides by x minus 3. On the left, it'll just reduce off. So that'll leave us with x squared plus 5x plus 4. On the right, we'll have to do some distributing. Okay, so we're going to distribute x plus 8 through x minus 3. And again, pause the video and do this as thoroughly as you need to. But when you are done, you will have x squared plus 5x minus 24. So look, on the left, I have x squared plus 5x plus 4. On the right, I have x squared plus 5x plus minus 24. So no matter what x is, these two things I have in red boxes right now are going to be the same. The x squared plus 5x's are going to be equal to each other no matter what. But on the left, you're adding 4. On the right, you're subtracting 24. So you are never going to end up with the same value if you took something and added 4 to it, or you took the same thing and you subtracted 24. So we'll put actually here that these two things are never equal to one another. So that means that the graph doesn't cross its slant asymptote. It can, so it just doesn't in this example. Okay, last thing, let's build a sign chart. So remember, the sign chart is largely constructed by the time you've come here. Your critical numbers are going to come from your vertical asymptotes and your x-intercepts. So in our case, those are -4, -1, and 3. And then 0 doesn't happen to be one of our asymptotes or intercepts, which means that we already know that when x is 0, y is negative, right? We already had that here when we found the y-intercept. So let's go ahead and use that. We are negative between -1 and 3. No non-negative factors, so the sign just flips every time, like so. And now off we go. So to the left of -4, that's here, right? The graph is entirely below the x-axis because the function is negative. But also don't forget, you have this slant asymptote to obey. So what your graph is going to do is something like this, where it's going to sort of approach and eventually get closer and closer and closer to that slant asymptote. Okay, between -4 and 1, your graph bumps up over the x-axis for a minute, like that. But then it has to come back down because it has another intercept. And between -1 and 3, it's below the x-axis, but don't forget, it's got this vertical asymptote to contend with. So yes, it has this intercept, but it will eventually come closer and closer and closer to that vertical line, okay? So you can smooth the shape out to make it look nicer if you want to, but that's the rough shape. Now, between 3 and infinity, so everywhere to the right of 3, the graph has to be positive. So you might be wondering, well, where is it, right? Is it like this? Well, no, it can't go like this because then A, it would have to have another x-intercept, and B, it would have to go negative here. Can it be like this? Nope, because then it would have to cross its slant asymptote, and we know it doesn't. So the only option that this function's graph has is to do something like this. Has no other option. Now, exactly where it does it, so you'll notice I'm not plotting any points. It might be higher up, like so. It might be tighter to the asymptotes, like so. I'm not too worried about the particulars. If you're really curious exactly how this will look, you can plug it into Desmos and see what you see. But the gist is this, that this graph is going to be sort of stuck between its two asymptotes, the vertical and the slant. So this is the last video that I will make on rational functions, but I will also post a sheet of practice problems for graphing rational functions. And I'm happy to discuss those problems with you in office hours. You can discuss them with Irina. And I can also talk about them in our class meeting. That's all I got for you on rational functions.